So is it visible?
Screen visible, is it?
Not yet?
No.
Okay, just a second.
Okay. Yes, it is visible now. Yes.
Okay. Right. So, very good evening to all of you. My name is Chiranjoy. I'm an assistant professor in the Department of Computer Science and Engineering. And today I'll be talking about digital image processing through linear algebra. I'm not sure, was there any talk on this particular topic of image-related applications?
Not yet. In the last week of this workshop, means next week, Gaurav Bhatnagar will continue this topic.
Okay,
First talk.
Right, right. So thank you. And so, any of you, I mean, the attendees, do you have any prior anybody working in this domain? Maybe are there anybody who is working in this domain of image or video processing as an application area? Are there anybody in the audience? Maybe you can just type in the chat window, just to get a sense of it. Okay. So, right. So let me start then. So today's outline of the talk is the following, where I will be discussing about the digital image, like how computer sees an image, and then image as a matrix, and then various operations on the matrix. I will be showing you examples on MATLAB. So all these, so that you can actually experience that, okay, if I add two such matrices or subtract two such matrices, what changes it reflects on the image itself. And then I will also be talking about some applications of image processing related concepts. And towards the end, I will be touching upon one specific area which I personally work on. One of my PhD students have the work that we have done together. So that I will highlight towards the end. In between, if you have any queries, please feel free to ask. So let me start by first defining what is a digital image. Okay. So as you see, an image is a visual representation of an object, a person, or a scene. A digital image is a two-dimensional function, f of x, y, which is a projection of a three-dimensional scene in a two-dimensional projection plane. Because the world outside is 3D, and when we capture an image through any image capturing device, so it's a camera, what essentially we do is we do a 3D to 2D projection. Now, once we do that projection, each of this location of this 2D image actually captures the intensity values, which is coded in terms of some range of values depending on how we represent the image. And when we see an image, say we use a computer or any display device for that sake to see an image, we actually see those intensities in a particular color or monochrome or whatever it is. Right? And when these values x and y's at every location is discrete in nature, then it becomes a digital. So if we go back in our in the older days when how the images are captured, right? So you see in the slide that there are this concept of pinhole cameras where the reflection of an object comes to a wall or a screen, then the artist used to draw upon it, right? This was the initial days of capturing an image, right? But it requires larger room and other type of devices to capture the light in a proper intensity, and then only the artists used to draw them, and that's how we used to get those images. Later on, technology has evolved, and currently what we see is what is now shown on the slide, where you see that we have the concept of from scene to data. So what has happened here, you see that there is this object and you have the camera lens. The camera lens actually sees the world outside. Now, when the light comes through the lens, it come across various type of filters. Okay, various type of filters is come across, and there are sensors which are placed up to the analog to digital converter that you could see in the slide. The previous part is analog in nature. That means the light and all these things are not yet digitized. After the analog to digital converter, where the conversion happens, the discretization happens there. Then the digital images is actually created, and then it is stored in a memory. Now, this memory can be of various type. You might be using these kind of memories in your mobile phone, or if you have a digital camera, or even the camera through which you are able to see my face today during this presentation. Everything is happening through a digital medium, right? So there is a discretization of these analog signals, and what you get is those discrete values stored in those locations, x and y location. That's why it's an f of x and y. In those locations, those discrete values are stored, and that is what we have, nothing else. But it is not only two-dimensional. Some of you might have cameras which has multiple links, and through which more than two-dimensional data can also be captured. And you could see that in your mobile phones, those who are having such mobile phones with this camera setup, you'll be able to see that you can do much more than this two-dimension. You're able to get the foreground object can be highlighted, the background can be blurred, and all those things you could see. Those applications are being developed on top. That is possible because of multiple such lenses are there, and this representation of the image is very, very important in this case, right? So the question is that, okay, this is what we could see, but how computer sees it, right? Because at the end of the day, whatever processing we do, we need a computer. In a sense that a computing device, that can be your mobile phone, that can be your laptop or desktop, a server or a high performance computing, whatever it is, we need to store it and present it to the computer. How the computer sees it, right? So here is an illustration on the slide. You could see that here we have a small, here we have an image, and this is the discretization of it. So here we could see that those black dots are representing some features. The white is representing the background. Okay. And now when it is stored in terms of a matrix, right? So what we see that this is nothing but a series of zeros and ones. These locations, individual locations, are called picture elements, or in short, pixels. Pixel is nothing but a picture element which actually stores the value. Now here in this particular case, it is zeros and ones. As I said, this is the discretization has already happened. Depending upon what the range of values that these images are having, we could have a binary image or a grayscale image or a color image. We will see those examples going forward. Right. So this is what computer sees an image as, right? So when we talk about such things, that becomes the challenging part. Here you see that there is a car. We could see that it's a car. But what the computer sees it, it's a sequence of these numbers only. That's all. Now, if suppose the task in our hand is to sense that, okay, is there a car or is this image having a car in it, then we need to make sense out of these numbers, right? We need to make sense out of these numbers and answering the question whether the image contains a car or not, only by using these values within this matrix. And this is only a portion of the car being shown. So that is why the task of understanding the image is more challenging. So as I said, like representation is important. So how we can represent it? And then a very simple example to understand. So this is the same image of the face with the zeros and ones. Now, if we want to represent this matrix, simply what we can do is, one way of looking at it is that we concatenate all the values row wise and then convert them into its corresponding decimal number. Okay, now what we have done, the image, which is the smiley image, has now become a one-dimensional array of a sequence of numbers. So we have kind of encoded it in terms of a vector or an array of numbers, where this particular array represents the smiley face. Okay, now once we are able to represent this image as a one-dimensional array, now we are free to do many operations on this array. So this is one type of representation. The good thing about this is this process is reversible in nature, right? So if we have such a representation, so the previous one is an example of image becoming data. Now, once we have the data, from the data, if we do a reverse process of it, we could get an image which represents some object. Here you could see that it represents a small outline of a house, right? But this is a very
Sir, what is this 0000?
Okay, so thanks for the question. So these are all you can think of like these are all intensity values. Okay, these are all values which are stored. So 0 can be thought of as a black, and or say 0 can be thought of as a white, and 1 can be thought of as black, or the value is there or not. It's kind of a binary logic. Okay, so whether there's any value is stored there or not. Zeros can be thought of as white, and black can be 1 can be thought of as black. Right? Just to give a sense that okay, there is a shape, some sort of a shape is there, and then we can actually play with those numbers. That's one important thing I wanted to highlight. Another thing, but there is a catch here, right? Now this is one way of representing it. Another way of representing it could be that okay, how many zeros and ones are there? Right? As you see that okay, there are 41 zeros and 8 ones in this image. This can be one representation. Or there can be another representation, row wise I can count how many zeros, how many ones are there. But there is a problem in this. Can you identify?
Yes, in that case, we don't know where are the ones and where are the zeros exactly.
Absolutely. Right? So this same representation can lead to a different image. What we want in terms of representation is that we should have a unique representation so that I can distinguish between two such images, right? If I say that, okay, this is an image of a cat, this is an image of a dog, right? The two represent, when I represent them, say is an array or in some representation, I should be able to all images of a dog, all images of a cat should be similar in nature, right? So if that is what I want, because otherwise I will not be able to distinguish these two things. So my representation of an image is very, very critical depending upon what is the underlying application I'm targeting, what I want to achieve, what is the question I try to answer. That is what representation is very, very important here. Okay. So going forward, this is what human vision is, right? We have an input, we have our sensing organs through which we see, we have our interpretation engine, it's our brain, and from that we interpret and conclude, we draw an inference that okay, this scene is about this, this is the object presenting an image, and so on. But when we try to see the parallel with the computer's vision, there also the input is an image, but here this what we are talking about is the sensing organ now is your camera. Now when we talk about the camera, we have just talked about it, right? It's a digital image. Now the interpretation engine is your computer, or again I should use generic term, computing device. That can be a mobile or your workstation, whatever it is. And then from that interpretation, we derive what is the content present in the image. Okay, now there can be many such type of questions that can be. I have talked about a few of them, saying that okay, whether what type of objects are present. You might have seen things like optical character recognition, where given file we are able to read, I mean, the computer algorithm able to read what is written. If you are using this Google Lens nowadays, if you could point out the camera to an outside scene, it is interpreting you and giving a lot of information about the scene outside and all, right? So there are many such things. But to solve those problems, right? To solve those problems, there are various fields of study. I wanted to make a distinction because today's talk is about image processing application. I wanted to make a distinction about, at this point in time, before we actually go into the image processing things, to give you a clear picture about and the distinction between various such fields which exist, so that you get a clear picture about what domain you are working on. Okay, so if you look at this slide, okay, this slide is talking about the interplay between various fields of study. On the left hand side, you are able to see an image which contains a horse. On the right hand side, you see a graphical representation of it with lots of triangles, geometric triangulation. Some you may be aware of, some of you may be aware of Pinhole triangulation, various other triangulation techniques to represent surfaces. So this is one such representation of this object present in that image. And there are various arrows which talks of various fields. So let me first start with the field which we are going to talk about, which is image processing. You see that the arrow is like this is a self loop. So when we talk about image processing, so for any such process or any such algorithm field, there is an input, there is an output. When we talk about image processing, the input to the image processing algorithm is an image. Output is a processed image. That is also an image. Now, what sort of processing we are going to do? That depends upon what is our task. You might be using various sort of processing. Let's say when you are sending an image, let's say in WhatsApp, if you swipe up, there are a lot of filters which shows up, right? And you tap on one of them and it enhances the color. Some of them do a negative of, create a negative of the image. Some of them might highlight certain portion of the image. Some of them might change the hue or the color or intensity, many such things. But to all of them, the input is the image that you have given or you have opened. The output is the same image with a modified feature. That is what image processing is all. Given an image, I get a processed image. Now, when I talk about computer vision, what is that? Computer vision is one level up, where you take an image or maybe a processed image or some feature about the image and trying to represent it in such a way that some questions can be answered based on that representation. Here in this image, given an image of an image containing a horse, a computer vision task, okay, I'm emphasizing on this term, a computer vision task, because this is not the task that computer vision does. Computer vision does a lot of other things also. In this particular example, one such task is to extract that object present, the prominent object present in the scene, and give it a representation in terms of triangles, which can further be analyzed with pattern recognition techniques, which or currently you might have come across terms like deep learning and all those concepts. Those concepts requires a representation to be very specific in some vector space. Now, the conversion of the image, which is a 2D matrix, maybe if it is a color matrix, then maybe it's a 3-dimensional. Take that image, convert it into a feature space, which is basically a vector space. And then in that vector space, the machine learning or the ML algorithm are going to operate. So the task of computer vision is to take that input as an image, give that representation in that space. And then using some pattern recognition or ML algorithms, draw some inference out of it. Right? So that is the important task here. On the other hand, there is another field called computer graphics, which primarily being understood for various type of animation, gaming, various type of special effects, which you can see nowadays in various movies and all. You might be aware of things like VFX and all, and currently there is a huge hype related to augmented and virtual reality, which is all about computer graphics and AI. So what computer graphics the field is to take that interpretation and create that image. So it's a reverse problem. This one way is your computer graphics operating, taking the representation, creating an image. On the other hand, computer vision takes that image, create the representation. So this is a two reverse problem that is going on side by side. Which is so this and then there is various type of geometric processing which can also happen on these triangles. If you suppose you want to calculate the curvature of those surfaces, suppose you want to create a 3-dimensional representation of an object from a 2-dimensional view of a person. Right? Nowadays, those works are going on in the field of computer vision and graphics, where you take one posture, frontal, maybe a standing image of a person, and then you create a 3D out of it. Right? For that, there are a lot of geometric processing may be required to calculate the curvature, to smoothen out certain noises. So then you need to work on the geometric property of the surfaces. Right? You might have to calculate the mean or a Gaussian curvature at various points, and then see the smoothness and calculate those derivatives and all those things has to happen. But for that, that calculation cannot happen on the image, right? Because that image is at a different space. I need the representation in such a space where I can actually operate on it, right? So that is the role of these various fields. So the beginning, right? So the starting point of all these are nothing but this this matrix representation of the image. From that, whatever I want to do, if I want to do image processing, if I want to answer certain question using computer vision techniques, or given a representation, I want to convert it to an image. At the end of the day, it's all about those matrices let me just go back a few slides. It's about this, right? So it's about this matrix representation which is critical, and from this we need to interpret, answer those questions, whether we are able to detect whether a particular object is there, a particular task being performed or not. And I just extend the concept a little bit here with, if it is a video, then along with the space, which is 2D or 3D, we also have the temporal information. So that information is also present. So maybe that is out of scope of today's discussion, but I mean, the concepts of this image processing and all can also be extended to process videos, right? So at the end of the day, it's about image as a matrix, right? So this is what the foundation of this discussion. Any question at this point in time before I actually talk about this processing techniques?
Yes, sir. At one point, sir, you showed that you are converting a binary matrix into
Yes,
a single dimensional array. So,
yes,
sir, so you were choosing some numbers 8, 33.
yes, this one.
Yeah. So, sir, is there anything special about these numbers, or we can choose any numbers, random?
Oh, no. See, I'm sorry, I didn't get detail into it. So if you observe this slide, so what we have is this part is clear, right? Every row, I am just concatenating these values to get a binary number.
Yes, sir. It is clear.
Now, if you convert this into its correspondence, let's say this one. So this binary number, so this is binary to decimal conversion actually. So all these binaries are converted into a corresponding decimal numbers. So this 000100, this is base 2, right? So this is a, I mean, this is a base 2 number. I converted into a base 10 number. That's all.
Okay, sir. Okay.
So maybe, yeah, I should have been more explicit. Sorry, I assumed that this part may be clear, but yeah.
No, I am
This is
actually new
basically
to this
a base
side.
2 number. So let me spend a minute here. So what you do is essentially these are all positional numbers. So you multiply every number by a power of 2. So this is multiplied by 2 to the power 0. This is multiplied by 2 to the power 1, 2 to the power 2, and so on. And then you add them. That's it.
Okay.
So for example, if I want to calculate any number like in our decimal number system, also it's a base 10 number, right? We can multiply individual digit by power of 10, and if we sum them, we get the number. Right? So this is a positional number system, and so this is basically a conversion from binary to decimal.
Now I understand, sir, what is happening.
Yes.
Thank
So
you.
that is why I was saying here that if I have a decimal number, because this is a reversible, so this has to be reversible, mind you. Otherwise, what I will get into this problem, right? Maybe two different images giving me a same, right? So I want a unique representation.
Okay, sir. I understand.
Is this clear now?
Yeah. Thank you, sir.
Yes. Well, any other question?
Sir, one question. How do you make this matrix?
Oh, I will show it. I will show this to you. Just hold on a few minutes. The demonstration is almost like is there. Maybe a few slides down the line, we shall see the demonstration. I will run a MATLAB code and I will show you how to do it. So, any other question regarding this, regarding the fields? But that part is, the distinction is clear, right? Image processing, vision, then there are application of this pattern recognition, machine learning, and all. So essentially, image processing techniques are used as a pre-processing, okay, to answer any such visual things, right? Whether there is a any object is present or not, who is there, what is happening, all these high-level questions start from these images, and there may be some processing required to enhance certain feature, certain properties of the image. So image processing as such is generally used as a pre-processing stage, which kind of enables these computer vision or higher level algorithms to perform better. Image processing, the role of image processing is that you might see, say for example, let me give you a say, you might have a very old photograph at your place, and you see that some of the places people kind of remove those scratches, color it to make it more enhanced, right? So those are all part of image processing. Input is an image, output is an enhanced image, right? All those are image processing examples, but it is not answering any high level question. If there is any high level question to be answered, that goes into the domain of visual analysis. Okay, so shall we move ahead?
Yes, sir.
Yeah. So I was talking about this representation, and precisely I think the question was there, how do we represent that? I will switch to a different window. So essentially, if you see, there are three types of representation that we have when we talk about an image. Okay. So there are these color images which we usually see. Essentially, there are RGB. There are various color models: RGB, red, green, blue, or hue saturation value, HSV. You might have seen in your printer, and now there are this cyan, magenta, yellow, black, CMYK representation. So there are many such representation, but at the end of the day, all of these are nothing but an individual two-dimensional matrix stacked one after the other. Oh, sorry. Light has gone. Just give me a minute. So this automatic switching of lights. Okay, so what we have? So we have these various layers of these matrices put together that gives us the sense of color. Okay, so for every location we have seen there are only not a single value. Now it's a vector of three values, R, G, B. Three such values are there, and everything put together when we display it, right? Using, so there is these display units what we see, what we have with us, this monitors or those televisions and all. They are internally equipped with those color guns, so that the specific intensity values can be created with specific signal. Those intensity values can be converted into an appropriate signal, and we get a sense of color. On the other hand, these individual layers are part of a grayscale image, where the values of each pixel is measured in terms of the intensity, and the value ranges from 0 to number of these gray levels. Generally, we have these 8 such gray levels. So 2 to the power 8 minus 1, so 0 to 255. The values confined between 0 to 255. 2 to the power 8 minus 1. And then there's another category which is the binary image, where the values are zeros and 1. Okay, so that is how it is. Now let me switch to another window where I will show you some demonstration in terms of this MATLAB. Okay. So getting a different. Let me stop sharing this one. Start sharing this. Yeah, are you able to see the window here with MATLAB? Yes. So again, I am making a small assumption of that you have some background of programming, but please excuse me for that, because I just wanted to show you the things, just not by talking about like this is how it will look like, and I'm taking MATLAB as a platform. Okay, so are there people in the crowd, I mean in the audience who have seen or worked on the MATLAB? Any one of you who have worked on MATLAB? May not be. Yeah, so it's a platform. Basically, the full form of MATLAB is actually matrix laboratory, which gives I mean, it's designed. It's breaking is the voice. Okay. Yeah. Is it clear now?
It is clear for me.
Okay. Okay. Voice is breaking for everyone. Okay. I think Ganesh is facing some problem. Ganesh, if you are not able to listen properly, please ping so that I can repeat those things. Okay. Right. So okay. So this is a platform which gives us this way to see things and do a lot of operations on images. And it takes, I mean, operation on matrix is actually designed in such a way that the operations on matrix are optimized. Okay, so what I am going to show here is that how image representation of various types happens, right? So let me, so the first two lines actually to show you that how images are being displayed. So here you see that I have read one image which is there. So this is a image, standard image used in MATLAB of cameraman. Okay, so this is the image that we visually see. Okay. Now, when I want to check what are the values, so how computer sees it, right? So what I do is I display the internal values of the matrix, and you could see that this is what the computer is experiencing, right? This is the computer is experiencing in terms of the values. You see that the values are within the range of 0 to 255 because it's a grayscale image, and in this window you could actually check what is the dimension of this image, and you could see that it's a two-dimensional image of size 256 cross 256. So it's a 256 cross 256 matrix, and what the computer sees is this image, and what we see is this, right, when these intensities are appropriately displayed. Now there was a question regarding binarization, right? So when this is a grayscale image, now when we convert it into a binary image, so this is how it looks like, right? This is how it looks like. Now the question is how this is being done. This is being done with it's a function, but the function works in a way that it matches the intensity values, and to see that whether whether certain levels of values are, if they're more than a certain intensity, is basically a thresholding operation. It will set the values at 0, and if it is below certain intensity, it sets the value to 1, right? So like that, you could see that the low intensity values are set to black pixels, and the high intensity values are set to white pixels, right? And we get a binary image of 0 and 1. And here also you could see that your image binary is a logical image. That means it has only zeros and 1, right? So, and when I display the content, this is what it has, zeros and ones only. And this is, you could see that, I mean, here I am not able to show you all the values like whatever is here, but at least you get a sense that the values are only zeros and ones. Now, what about color images? right? So this is what this is a color image, and you could see that if I look at this variable IC where the color image is stored, you could see that this is a 486 cross 732 cross 3. Now this 3 is nothing but RGB. These are the 3 layers which are there, and the one which you see here is a combination of all these 3 put together to give you a sense of color image. Okay, now but can we access the individual layers? Yes. Right? So how the computer sees those images? The computer sees it as this is the red channel. So if I just look at this, so this particular notation denotes that I am looking at all rows, all columns of the first matrix. 3 matrices are there, R, G, B. The first matrix is R. So I'm looking at the R matrix, and this is how it looks like. If I just, it is just like a grayscale image that we have seen in the beginning, like this. So the color image, which is this one, when I look at the red channel of it, I could see this. When I look at the green channel, I could see this. When I look at the blue channel, I see this. And you could see now that all of these 3 individual layers itself has certain important features. Here I could see that the highlight component of it, right? The glossy part of it, these kind of glossy parts, those are coming out from the red channel. Whereas the shadow parts are more prominent. These shadow parts are more prominent in the blue channel. Right? So if I want to access or want to extract, want to emphasize on certain type of features, I can individually work on these layers and then combine it to give me a sense of a processed image, right? So essentially what our image processing algorithm does is it takes these matrices, operate on them, and extract or try to enhance or boost up those individual features, right? So if I want to binarize, I can binarize. Let's see, if I binarize the red layer, I could see this. I can binarize the other layers also. Let me change the value. Let me binarize the blue layer and see how the changes going to happen. So previously, I was binarizing the red layer. Now I have binarized the blue layer. Now you see that if you compare this, right, you could see that most of the pixels are of darker intensity. So only the highlight which are there on the skin of these fruits, those components are being now shown here because that is the component which is available more than the threshold. If I change it to the green layer, I could be able to extract some other type of features, right? Other type of features. See here we are getting the shape of it, right? Which is coming out of here because there are number of dark pixels are less here. So only those components are being highlighted and we could get the shape of this object, right? Just by one simple comparison operation on this matrix gives us a new image, and now we can play with this image, right? So let me now go back to the presentation. So I will be going a little bit back and forth, so please excuse me on that. But if you have questions, please feel free to raise so that I can. So now the presentation is visible, right?
Yes, sir.
Yeah, great. Right. So this distinction between gray level, binary, and RGB, this part is clear, right? And how we can access this by writing simple. And this is not only on MATLAB. There are many programming platforms which are available if you are comfortable in MATLAB or R or other say Python or something. Every such programming platform has that. If you are interested in working in this domain of images, you should know one such platform and then develop your skills on it. Right. So now what sort of operations that we can do? Right? That is the next question. So we now have the matrices. Now we want to operate on these matrices, right? So basics operation that we can do in two matrices are possible. Now we just have two matrices. We can do add, we can subtract, we can multiply, we can apply various type of transformation, and each of them, right, will give us a new image, which depends upon what we want to do. We shall be operating on the matrices accordingly. So the basic idea is that we have two matrices, A and B, and we want to operate. We can add A and B, we can multiply A with B, and so on. The basic properties of matrix addition, multiplication, subtraction, all those properties, mathematical properties, holds true here, right? And so when we try to add the dimension of the matrices, when we multiply with the identity matrix or doing a transpose, all these properties holds good. And we as an image processing person will try to see that how those properties can be utilized to enhance certain features of these images, which can help us to answer the further questions down the line, which is required, may be done through various computer vision and machine learning algorithms, right? So that is what we try to see. Now, again, let me go back to the mathematics. I hope it is visible.
Yes, sir.
Yes.
Yeah, please, I'm just asking this, please don't mind, just to ensure that all are on the same page. Thank you very much. So the basic operations on matrices. First thing is addition, right? So we want to add. We want to add two matrices and to see that what happens to the resulting, right? Given the fact that we have an image, and the image we can access the individual layers of the image. So let's see what happens if we add two such matrices. So this is the same image that we have. And what we are doing here is, you can very much understand it now. We are adding the green and the blue layer. We're just adding these two layers and see what has happened. There you might have seen these type of effects, right, in many such filters that you use. Which gives us something like enhancing certain features of your, or maybe converting an image into a sketch image. Those kind of filters you might have seen. This gives me some sort of an outline. You could see that this gives a sense of that, okay, maybe this is something like a hand drawn or a pencil drawn image. Somebody has drawn it with a pencil. Simple effect. What we have done, we have taken an image, extracted the green and blue layers, add them, we get an image. We have not done anything else. Simple addition operation. But the resultant is an effect which is giving me a sense of, okay, this is something maybe somebody has drawn it with a pencil. Right? So these kind of nice illustrations we can create. But there is a problem here. Can anybody identify? Based on the operation that we did, there is, and the very definition of image, there is a problem. See this IR1, right? The result, okay. These are two matrices. The resultant is a matrix of same dimension. Obviously, it has to be. So this is this 486 cos 732, which is the same dimension as that of my input image, which is IC. But it has 3 layers. I just took 2 layers out of it, add them to get another matrix. That is also of 2 dimension. But there is a problem. Although it is not visible, but there is something which you have to be careful of. Can anybody identify? Let me give you a hint here. You need to think about the gray level values.
Sir, can you repeat the question?
The question is, I have an image of a color image. Now I just extracted the two individual layers and we added them. And we got a 2-dimensional image which is shown here on the screen. What I'm saying is that there is a problem, something which we should have been careful about. Although it is not apparent here, internally it has been taken care. But there is something which has happened while we added those two matrices. The hint is that you need to think about the range of values. Let me be very more specific.
It's like order of matrices.
Pardon?
It means related to order of matrices.
No, the values, the intensity values.
Okay.
The intensity values. So what is the range of values in the green channel? Zero to 255, right? Pardon? Can you be a little bit loud, Jayakumar? If you are speaking. Yeah, so see this individual layer, this green, red, blue layers, they are all of certain range, right? That is also a gray level image, and we know that gray level image has a value 0 to 250. Now, my green layer also has values ranging from 0 to 255. My blue layer also has a value 0 to 250. Now, there can be two locations where when I add, in addition, what happens, I add element by element, right? So the range may go beyond 255. There is a possibility.
Yes, sir. When we add two numbers.
Right? So we need to be careful here that, so here what has happened internally, the range has been trimmed, the maximum range is made to 250. But while we do such operation, we should also be careful about these intensity values, and that may also help us in extracting some interesting features. That one I just wanted to identify, highlight, because this is just a simple addition of two matrices. But in an image space, this is actually pushing the intensity values beyond 255. So we should be careful about it and make appropriate adjustments. Okay.
So how we will fix this issue if the range is more than 250?
Pardon?
How we will fix this issue if the range is more than 250? Means after getting two entries, we are getting a number that is more than 250?
Right. So we can impose certain thresholds. That if the values, we need to add some more lines of actually conditions. That if it is going beyond, we should not I mean, that part is actually been taken care internally. What you see here, the values are within the range of 0 to 55. Okay, your resultant value are less than, I mean, most of them are actually 255. You could see that. If I make it, can you see the values?
Yes, yes.
Yeah, so most of the values are actually 255 because the addition of these two matrices have actually taken it more than 255. So if I change it, no, if I change it, let's say if I make it red and blue and run it.
Okay.
So see here, some darker components are coming up, right? So that is how we need to be sure about what feature we want to and then apply things appropriately. Let's come to another operation, subtraction. Again, two matrices, same dimension, we just do A minus B. Now, what is expected? Can you tell me what is expected? See, addition means it's looking at, it is boosting up, right? So subtraction obviously will do the reverse thing. It should highlight only the difference between the two. If there are difference between the two images, that difference should be highlighted. The similar things will cancel out to 0, isn't it? That is what is expected. Again, this is the image. This is green minus blue. So what you see here, the blue had more darker component. So from the green, I remove those dark components. So it gives me a different texture altogether. Right? I can change it. I can change the values and play with it. I will show you one example of this difference operation. Here you see not many things are highlighted because the green and the red channels are almost similar in nature in this particular case, right? But if I subtract the lighter component from the darker component, you could see appropriate features are coming up, right? So there mostly it is the black components are. What I am now going to show you is, suppose with this example, I want to extract these grains of rice from this image. That is my target, that I should extract these grains and I want to count how many grains are there and all those things. Second level of answering. I want to achieve that. So what I have this image of this rice grains, right? I want to extract them. So what I do a different type of operation just because what I need, this is a matrix, say this is a matrix A. If you want to extract only the rice grains and you want to achieve it through a subtraction operation, what do you think that your matrix B should be? So that if I do A minus B, I get the rice grains. Can anybody tell me?
So that means something that does not represent the rice in this image.
Right. So without rice, right? If I have something without rice, and I mean the same background, and if I have something on rice, if I subtract the without rice component from it, right? So I get the remaining part is my rice. That is the sense, right? So what I need what is known as a background image. This is the thing what is called as masking. Okay, so what has happened? So I have this background image. Now what I do is I do a subtraction. I get this image and I do some sort of a contrast change so that I get this rice grains with me. Then further processing has to happen. I am not talking about those processing. How to count there? You can have, I mean, you might be having the question, how to count now, how many rice grains are there? So what I need to do essentially is to see that how many such white color blobs are there, then count them. So that's a different set of processing which is there. So that is a little bit beyond the scope and the timing that we have today. But I just wanted to give you this intuition that a simple matrix subtraction operation, if done properly with proper order and some adjustment here and there, can give you a very interesting insight about an image, which can help you to answer certain questions. Now, somebody might ask a question that, what is a big deal in counting rice grains? Well, who will count rice grains then? But this application can have, this very thing can have, if you want to count, let's say how many, your cells are there in a microscopic image, how many objects are moving in a particular territory. All these concepts, all those questions has answer to this very basic subtraction operation. We need very further sophisticated operation after that, but the foundation is this, that there is something called as difference image, and this difference actually gives us this these individual objects which we can further do this. And you can see that further processing will give us more distinct existence or instances of these blobs. And blob is another abbreviation which is called as binary large objects. So these are all binary objects because these are zeros and ones. That's why they are called as blobs. Okay. So a quick application of this is negative of an image. You could probably have seen negative of an image being digitally created. So this is an image, input image, and essentially a negative means that if you look at a color representation, the negative image is basically the complementary color. So the range of values is 0 to 255. So the complement is that you subtract from 255 that value, whatever intensity you get, it is the complementary color, right? So what I did, I just subtracted from 255. This is the negative. Simple one-line subtract operation. What you get is the negative of it, right? So these kind of filters, now when you see in your applications like say WhatsApp or Instagram or Facebook, now you will kind of appreciate that, okay, this is nothing but a matrix operation. Okay, that is my objective of this concept. Then comes multiplication. Okay, so in matrix multiplication, very standard, two ways we can do. Either we can multiply two matrices of this row and column concepts, or we can multiply each elements of that matrix with a scalar, or we can element by element matrix multiplication we can also do. So three ways we can do. Multiply a matrix by a scalar individually, all elements, so that it will scale up to a different, every intensity values will be boosted up or down. Or it can be matrix multiplication like the row, column, that way. Or there can be element-wise matrix multiplication also. That element-wise matrix multiplication gives us the nice way of masking. Again, another application of masking is this. So let me show you the example, and while it runs, I will talk about it. So essentially, again, that coin image being loaded here, and here you see that similar mask being created. Okay, again, this is the binarization of it, and you see that like what we did earlier by picking up a threshold and converting into a binary image. This is again converted into a binary image. So this is my mask image. Now, when I apply this mask onto the actual image, I could extract those components. Right? These coins are now extracted. This is the operator, which is actually an element-wise multiplication. So what has happened? All the values which are 0, element by element, it got multiplied with this matrix. So multiplied by 0, all those things have become 0 here, so they become black. Those, the white pixels are 1, they also get multiplied with these objects, and the same intensity value is being copied here, and what I get as a result of this element by element matrix is this objects will extract. Now again, I can do counting, I can do various feature extraction, I can answer many such questions. Okay. Another effect I wanted to show you is this green screen effect. You might have seen this green screen effect where your news readers are sitting in front of a camera and the background is changing like the cityscape, or many such things are happening. Again, simple matrix multiplication can lead you, give you such kind of effect. Okay, here the one I am going to show is not that accurate because again, it might require, okay, this, okay, just a second. No problem. So what I have shown here is that some values here. These are thresholds. Let me give some value. So here you see that with these kind of, so this is an image with the background, and we could be able to kind of fill in with the background image. Okay, we can change this, play with this threshold a bit to exactly calculate what is the kind of the value that we are looking at. I can add on some more values here. Say if I'm looking at the green channel and the blue channel also, it may give some different result. So it's able to extract only the foreground object and then I can superimpose an image at the back. These kind of things can also be done. With matrix multiplication, you can actually flip an image. So this is an input image, and we all know that if we have an off-diagonal element, and if we multiply that, we can actually flip the image. Right? This is the flip of an image. So those things can be done. So let me now, these are the various concepts of various type of operations that are possible. Let me now just switch gears and let me stop sharing on this. Let me go back to the presentation and maybe show you something which is maybe which we have done in our group, which is essentially representing image content. So far what we have seen that an image is a matrix and we could extract features out of it. We could enhance certain features out of it. Now, what I'm going to show you now is that an image can be, we talked about the representation in the beginning where image converted into a binary number, then the binary number converted into a decimal. Here we are going to talk about one such representation, but now it will be represented as a matrix, as an adjacency matrix of a graph. And then that on that adjacency matrix we are going to operate. Okay. So here is one such application where we were trying to understand and interpret building for floor plan images. Okay, so this is one such example is this, where this is an input floor plan image, and the application that we are working on is trying to find out that given an input image of a floor plan, we want to retrieve similar such floor plan. Now, what is the similarity here? We want to retrieve or search floor plans from a database which are having similar number of rooms in it. Okay, similar number of rooms and orientation and the connectivity and all these things we want to capture. So, for example, if this is an input to the system, we want to retrieve similar such floor plans. That is the notion of similarity here. Now, the question is that how one can achieve this, right? Because this is an image and this is the matrix that I am going to have. So what I am trying to achieve from this is that can I represent it in a way that will help me to answer the question that two such floor plans are similar in terms of a property. Okay, so what we did, we use other image processing techniques which I have not discussed today, and extracted the rooms from it. That means I am able to extract the rooms from here. The room and its layout I am able to extract, and I will be able to and then represent that as a graph. Here you see that these nodes of this graph are the rooms itself. Okay, the 0 is the floor plan itself, and all these other numbered nodes of the graph are nothing but the rooms. And we try to embed them into a feature space which help us to distinguish between various type of floor plans. Here in this scatter plot, the red, green and blue colors denote the various type of rooms, and using machine learning techniques we were able to distinguish between such rooms. So what we did, so this is basically the spectral component of it, where we use the concept of eigenvalues and eigenvectors. So that we come here. So what we have, so this is the segmented room. Okay, this is the segmented room. Here you see that the rooms are numbered 1, 2, 3, 4, and there is this adjacency matrix which is created out of these rooms with a sense. So there is a concept of adjacency in terms of whether two rooms are connected to each other via any door or not. So based on that, we created these adjacency matrices, represented them as a graph, and then so this graph is actually nothing but this adjacency matrix, and then we extracted features from this adjacency matrix. Okay, so this is the graph, and we have this representation. So essentially what we have this feature space where we do this spectral embedding. We have this n eigenvalues of that adjacency matrix, and then from the covariance matrix we have this representation, and these are all happening on the adjacency matrix that we have. Okay, and then we calculate this eigenanalysis on it, and this top three component feature vectors, top three eigenvectors, they are actually comprising us the feature matrix. Now the question can be that why these top three and all? This has been empirically found out that this gives us the optimal result, and in terms of the speed also, so that we do not the number of comparisons are also less in terms of while we match two such floor plan images. Okay, so what has happened now? Your floor plan image is now represented as these feature vector in this three-dimensional feature space. And then what we did, so this actually give us the performance enhancement. And then this was the original data space. What we did, we using this spectral embedding, we create this new pattern space where the similar layouts are clustered. That means this is an illustration. This is not exactly how it is being done, but this is an illustration of it, where the spectral embedding is actually helping us to give us this nice clusters being formed. And due to this clusters, now we can actually identify the separating hyperplanes across these clusters, and using those separating hyperplanes given an input. So what has happened now? My floor plan is essentially a point in this vector, in this high-dimensional feature space. So this is what a feature representation is on. My floor plan converted into a matrix. Now that from this matrix, we actually extracted those rooms. Those rooms are represented as those graph by the concept of connectivity. Then this adjacency matrix of those graph, we did this eigenanalysis, through which we have this spectral embedding of the feature. And in that feature space, my one input image is now a point in that feature space. This is the concept of in this feature embedding and all. And now I can find out, given 2 points, I can find out some distance between them. Closer the points are, similar they are. Right? So that is how, that is the notion with which we actually identify similar floor plans. And so this is the similarity metric we used, and this is the component vector, which is the query, and D is the one which is from the database. And we are able to find out the similarity between 2 points in this feature space. Right. So now that is more, let's say, mathematical in nature, but this whole process of embedding them into this feature space is what requires this image processing, then vision techniques to extract those features and so on. So this is one such illustration where you see on the left hand side is the query, where we have the floor plan. The intricacies of the floor plans are being updated. I mean, those intricacies are being removed, just to give you the illustration. And then this is the rank 1 image, which is same as that of the query. And you could see that this is the rank 2 image, where you could see that there is a similarity in terms of the layout, but it is not. That's why it is rank 2 in terms of similarity. And then there are several other lower rank gradually things with the shape of the floor plans, which are very, very dissimilar. You could see that as compared to rank 1, rank 5 is very, very dissimilar. The rank 4 is also very, very dissimilar in terms of the feature space. Okay, I mean, even in the look and feel also, you could see that all of them are quite different in nature. That's why they are ranked less, I mean, lower in terms of the similarity. Okay, so that is something I wanted to kind of highlight, that with this various type of matrix operations that we use, we can solve actually various high-level problems also. And these eigenanalysis have been significantly used in terms of phase recognition, where there is a concept of this eigenphase. Then also being used in video representation and video content understanding in terms of traffic flow, in terms of crowd flow, and many other things, other places where this eigenanalysis of the spectral embedding features being extensively used. So I think this is an important area to explore also. With that, I conclude today's discussion. If you have any questions, maybe we have some time for question answer, so we can have some discussion on that.
Thank you very much, Dr. Chiranjoy, for wonderful talk. Any questions, participants? Any questions?
Sir,
Yeah.
thank you for this wonderful talk. I want to ask one thing. This talk is really interesting. So, how we can get more about these things, image processing? I am seeing this first time in this.
See, there are, I mean, nowadays there are many online resources which are there. which you can use to understand. Even if you, so two things you need. One is that the concept level, well, for which you can refer various materials, and the other part is to do hands-on, like what I have shown you using the MATLAB. So you also need to do some hands-on things to understand the concept, to implement the concept, and most importantly, to realize and visualize that yes, this is what is going to happen if I operate this on one specific operator on an image. So you can start with many such in NPTEL. There are many such courses which are available on image processing, which are available in YouTube. You can freely access them. There are many such tutorials, but what I would do two things: you concept as well as hands-on also you practice. Then only you will get a sense of what is happening. There many books are also available. Very standard books are also there, like the book on image processing by Gonzalez is a very, I mean, it's a kind of Bible for people who are working in the area of image processing. Very standard books are also available.
I would like to add that this topic will be taught further by Dr. Gaurav Bhatnagar. Chiranjoy, is this work is related to Gaurav Bhatnagar's work as well?
Actually, I mean, we do have a common PhD student who
Okay.
worked on this area, but I think probably he will talk more about maybe he also worked on the area of image processing, core image processing.
So actually his
things.
syllabus is image processing, applications of linear algebra in image processing. So he
Right.
will be taking lectures for full week.
Oh, okay. Then probably I think you will get a lot of. I think whatever I told today, he will explain it in details. I think that is that. Then you will come to know more about it, because my focus is basically to give you a kind of glimpse of his. These many things are possible, and very simple examples I have used today. Not much complex, just a very small examples, just to give you the kind of trigger the interest. I think that is what my
Yes.
target.
So you can take his talk as motivation. Fourth week's lecture by Dr. Gaurav Bhatnagar.
Yes.
This is
Please,
really wonderful.
please attend that. He will, I think, definitely explain things in much more details.
Okay. And Dr. There are requests for presentations PDF. Can you provide that?
Yes,
to participants? Okay, so please
what I will
email.
do is I will create a PDF and share with you. You can share with us.
Yes, thank you very much. Any other questions for Dr. Chiranjoy? Okay, if not, let me thank the speaker once again. Thank you very much, Dr. Chiranjoy. And we are going to end this call here. We have one announcement for participants that tomorrow we will continue our discussion on linear algebra. The lecture is at 5:30 p.m. It will be delivered by Dr. Anupam Singh. He is associate professor at IIT. Okay, he will be taking lectures for full week. Okay, so thank you, Chiranjoy. Bye.
Yeah, thank you. Thank you.
Bye. Thank you very much. हाँ बोलो अब भी खत्म हुआ हाँ